All right.
Rustin, ready? Ready?
I'm ready. Welcome, everybody, to our session. Thank you for attending. We hope you've had a good day so far, or morning so far, or night, depending on where you're logging in from. It looks like we've had a pretty diverse crowd, and that's pretty amazing. So this is Develop Career-Ready Graduates Through Project-Based Learning. And what we hope to show you in the next 30 or 45 minutes is some project-based experiences that will help your students learn some of those, what you might call technical skills or hard skills, as well as the soft skills that we're all trying to teach our students. My name is Rudy Ottway. I am an associate professor at Murray State University in Murray, Kentucky. Murray, Kentucky is situated in the far western part of the state. We are sort of sandwiched between St. Louis, Missouri, and Nashville, Tennessee. And this is my colleague and friend, Dr. Rustin Webster. He's an assistant professor at Purdue University, specifically at the Purdue Polytechnic in New Albany, Indiana, which is just across the river from Louisville, Kentucky. In the next, again, 30 or 45 minutes or so, we're going to give you a little bit of background about us and how we came to our teaching roles. We have a lot of project-based learning examples to give you. We want to give you a little bit of terminology about project-based learning and maybe some of where we're coming from on this. And then toward the end, we would like to just give a quick wrap up, maybe some project-based learning tips and tricks, or just a few things that might help you if you decide to implement some of these in your programs or in your classes. And then, of course, at the end, audience Q&A. However, this would be much more engaging if you want to go ahead and add your questions to the Q&A tab over there on the right. And Rustin and I will try to moderate that and look at those. If it's a great time to go ahead and answer that question, we'll try to grab it. And if not, we'll then maybe try to save a little time at the end to get to your Q&A. So thanks for being here, and we hope that you learn a lot about project-based learning. Again, my name is Rudy. I'm starting my 15th year at Murray State University, and I am an engineering graphics and design undergraduate from Murray State University. After I graduated, I moved to Huntsville, Alabama, and worked for a company called Science Applications International Corporation. And we created CAD models of military hardware, and we used those for signature analysis. This is actually where Rustin and I first met. I was working full-time in Huntsville, and Rustin came down from Murray State University, where he was an engineering graphics and design student. He came down as an intern and worked for SAIC. And then around 2006, my wife and I, before we started our own family, we wanted to move back closer to this area because my family is still in Paducah and my wife's family is in Hopkinsville. And this position at Murray State opened, and we thought it would be a good career move. So again, 15 years later, here we are on this adventure that's been a lot of fun and challenging and very rewarding. Our engineering graphics and design program is a 4-year Bachelor of Science degree program. It's heavy computer-aided design based, has a focus in mechanical design. So we're teaching SolidWorks, AutoCAD, Creo, and because of the recent pandemic, we had to do some adjustments, and we implemented a little bit of Onshape into our curriculum. Some of the courses are ones that I teach there. These range from freshman level all the way up to senior design, and the majority of them are SolidWorks-based courses, and we'll talk a little bit about some of the projects that we perform in those courses.
Thank you, Rudy. Welcome, everyone. Thank you for attending, just as Rudy said also. I'm starting my 5th year here at Purdue University, specifically Purdue Polytechnic, New Albany. As Rudy said, it's in New Albany, Indiana, and we're right across the river from Louisville, Kentucky, which most of you might know that better. I'm actually part of the School of Engineering Technology. We have many degrees or majors. Mechanical engineering technology is my major emphasis, or where I teach most of our classes. We also have computer graphics technology, which is in control of the CAD curriculum. And I also teach most of those classes here in New Albany too. So I split my time between MET and CGT. As Rudy said, we met in Huntsville, Alabama at SAIC. After that, I actually went and worked for a company called Intuitive Research and Technology Corporation, or IRTC. I did that for roughly 8 years, designed various solutions for multiple branches of the armed forces, anything from Army to Air Force to Navy. Customs and Border Patrol, and I'll show you some snippets of some of the projects I worked on the next slide here. After getting my doctorates actually for the company, I actually came back and I did some business development too and worked on some commercial products. We tried to diversify a little bit in our company. But this slide kind of gives you an overview of just the vast amount of projects that I got to work on in 8 years. Intuitive was a special place. They, I guess they didn't really look at age as long as you could do the job. And it allowed you to have ownership of the projects that you worked on. So I worked on anything from cargo restraint systems for cargo planes, the C-27 Spartan specifically. Almost all your gun mounts in any helicopter was designed by our IRTC. Worked on a health monitoring system for the THAAD missile, which is the bottom middle there. Got to work on a Avenger relocation project in Washington, D.C., which was really special. I did some work in virtual reality. That's actually what my doctorate was in, to see if soldiers could learn better in a virtual environment versus your standard instructor with PowerPoint in front of a classroom, which is probably why I do a lot of project-based learning here at Purdue Polytechnic in Albany now. But I got to work on a lot of neat stuff, and it was a fun experience. But now, like I said, this is my start of my 5th year. I do teach most of our CAD classes here, or design classes is what I actually prefer to call them. We are a SolidWorks house here in New Albany. Purdue in general, some faculty teach Inventor, some has Fusion 360, some have dabbled in Onshape. But here in New Albany, I'm a SolidWorks person. We do a couple weeks of AutoCAD also. We have some laser cutters, and that's why we do AutoCAD. But the 4 classes that I'm going to present projects on today, you can see there's Tech 120, CGT 163, 110, MET 102, and MET 302. I also wanted to mention that I do a lot of stuff with certifications. We use the CSWA as a final exam in our intro CAD class. And I also do the CSWP in the junior level class, along with recently adding the additive manufacturing exam and the sustainability exam to a materials class on plastics, actually. So if anyone has questions on that, I have quite a few of them, certifications, so I'm happy to talk on that.
And if I can brag on you, Rustin, you are a certified SolidWorks expert.
I am. Yeah, I am. I don't. It's been a long time since I've used it at that level. Now that I teach it at a freshman level, but yes, I was or am. I'm also an active researcher. My interest is in ET, or engineering technology outreach, and ET education, specifically with focus areas in design, pedagogy, and then technology use in the classroom. Many of the projects that I'm going to showcase today were also studied for their impact on students' professional skills. And when I say that, you could think of engineering design, problem solving, communication, and teamwork skills, if that's easier to understand. Me and Rudy have actually worked on a couple papers together also at conferences and journals. We understand that there are no universally accepted definitions for many of the terms that we're going to use today. So Rudy and I thought it was important to provide some short and simple definitions to enhance clarity and consistency among us today as we discuss this stuff. So the first one that we wanted to present, there's 3 of them, but the first is project-based learning. I think we all understand it's a form of active learning, right? However, there is some distinctions from active learning that can be made. And for me, and I don't want to speak for Rudy, but for me, it's the extended length of time that students work on the challenge or the project. And when I say that, I do not mean hours, and I don't even mean days. I mean weeks and or months. And you're going to see most of my projects that I present today are 16-week-long projects. So it's a big distinction. And then second is, the students need to produce a realistic product and or presentation. All right. The second term that we want to define is active learning. This is a use of learning-centered instructional methods. However, I would rather think of it as learning is the emphasis, right? So a lot of times people would say this is a student-centered instructional method also. They're used interchangeably. And at the core, students are engaged and there's dynamic involvement in the learning activity. And finally, since I just mentioned student-centered learning, I'll present a definition for learning-centered paradigm. And And for this, the discussion generally center on the use of active learning instructional methods, all right? And I want to mention that, project-based learning is not the only method of active learning, right? So, group discussions, problem-based, and there's others too. However, the instructor helps the student learn, all right? So it's kind of flipped. It's not that the instructor teaches the student, it's the instructor helps the student learn, all right? So they're kind of working as partners here. And also, I like to mention that a lot of times when we talk about student-centered learning or paradigm, people don't think you can have traditional instructional activities such as homework, exams, quizzes, and lectures. I don't agree with that. I don't think Rudy does either. We include many of these in our project-based learning classes also.
Excellent. Thanks, Rustin. And just to sort of dive into the meat and potatoes of what you're here for, I'm going to show you some of the project-based learning examples that I use in the engineering, graphics, and design curriculum here, and then we'll switch over to Rustin, and he's going to show you some of the ones that he does there. Cassie had a great question about projects. Could they be simplified for use at the high school level? And I said, probably so. I think maybe after you see some of these, hopefully it will inspire you, or maybe you'll be able to see how these relate to what you could do inside your classroom. And of course, Rustin and I would certainly be willing to help give you some tips and tricks and ideas on what you might do at the high school level.
Rudy, I'd like to chime in. We didn't really mention it. So I know for the 4 projects that I'm going to present today, I'm very detailed in the instructions that I give students. I always create a project description handout. I use Dropbox for all my classes. I am happy to share all the material with anyone. I've actually done it because of other conferences and stuff like that. So if anyone wants to reach out to me, I would imagine Dr. Ottway or Rudy would be the same. I'm happy to share the material that we have with you all, which can save you a lot of time. So.
Yes, and speaking of sharing, just to go ahead and address, our email addresses are at the very bottom. There's probably a way within this virtual summit to access us, but our email addresses are supplied at the end of this. If we'll get to that last slide, we can provide that information for you. This is an overview of the design build projects or project-based learning experiences that I use. Rustin may use a similar format or something slightly different, but I ask my students up front to generate ideas of what they think they're going to do, take some time to think about it, and then I have them move into some sketching and do sometimes 3 to 7 pretty detailed sketches, and I provide them examples of what I expect out of a detailed sketch and what is maybe not detailed enough. And then from there, we move into the CAD modeling stage. In most of my classes, that is in SolidWorks. I have found that when students provide those detailed sketches and sort of think through some of those things on the front end, it actually enhances and increases the speed at which they can produce the 3D model. And then once they feel like they have their model or their design finished, we have an oral discussion. It's a preliminary design review in front of the entire class that gives them an opportunity to practice some of those soft skills, but also hard skills, and talk about their design. And then based on feedback from that preliminary design review, they will go back and refine the CAD model. And usually these are small things that they tweak. Then they go into full manufacturing to produce either a prototype or then what might be their final version of whatever it is that we're manufacturing. And then we have a final design review, sort of a wrap up and a reflection at the end of that. So the first project that I want to show you, we've got some images of these actual projects on the next slide, but the first one is called the Catapult Project. This is a small desktop catapult. Students are working in teams of 2, and they are given one 12-inch square by 1/4-inch sheet of plywood. We do supply dowel rods and glue and 2 rubber bands to power their catapult, but they are using SolidWorks to design this. They're working with a partner, and then they're going to produce this on our Epilog laser. We have a small Epilog Mini. It's 18 inches by 12 inches. So that's what we have in our prototyping center for this project. Students will also learn a little bit of CorelDRAW. And you can see here's an example of what a student might do for that catapult. And we've seen a variety of designs. The one on the left, of course, is the SolidWorks screenshot, and the one on the right is the physical one that they've actually built. And if you're wondering what we launch, sometimes it's a marble. One of our other faculty uses those big sidewalk chalk pieces, and she cuts them into small cross sections. And with the marble, a lot of times we just go for distance, who can launch it the farthest. But with the chalk, sometimes we go for accuracy. And we have found that if we slightly wet the chalk, when it hits a paper target, we can see exactly where that piece of chalk lands. And so they're trying to hit, some sort of bullseye. On average, these probably launch around 25 feet. The one that you see here, if it's slinging a marble, it could launch it anywhere from 50 to 70 feet. So you might do a few tests inside, maybe a few tests outside to kind of get an idea of how these things are going to launch. Here's a couple of other examples. Again, just to show you a little bit of a variety on these. Again, students get one sheet of plywood and they have sort of a one go at it to see what happens. It's really great for them. Let me jump over and see if there's a question there.
I don't see any. I got it pulled up too. I don't see any right now.
Perfect. Thank you. The second one, or another project to introduce you to, is what we call the Golden Reunion Project. We do this at the 200 level in a group of sophomores. This is a collaboration that we have with our alumni relations office. And if you're wondering where could I find some projects, you could look around to different offices if you're on campus. If you're at the high school level, you could just talk to your different faculty and start to ask them, do you have any projects that we can engage in? That's sort of how this one started. So at Murray State University, every year for homecoming, we have a alumni reunion, and the Golden Reunion is those people who have graduated 50 years or more. And our alumni relations office asked, could your students design a unique gift for that group of reunion goers? And so we said, absolutely. And the alumni relations office really thought it would be great if it was designed by the students for the previous students. And so for this, we're again working in teams of two. I like teams of two. That seems to be the best workflow. Sometimes when you get that third wheel, you get one student that doesn't really do anything or contribute, and it's sometimes difficult to assign tasks that way. Again, they have access to the Epilogue laser, but in this case, they also have access to our prototyping center where we have a variety of 3D printers. I encourage them for this task to use our Affinia. We have the 400, we have the 800, and we have the H+1s. We have a variety of these Affinia machines, and they have to learn how to use 3D printing while they're also designing this Golden Reunion gift. This is about a 3 to 4 week project. And then we present to representatives of the alumni office and to representatives of that Golden Reunion. So last year was the year that they graduated in 1969, celebrating 50 years. And this is the final. This is what they selected as the final gift. It's a box coaster set. So in the image on the left from SolidWorks, you can see that it has a red oak box that's got laser engraving on it. And the 50th anniversary is the logo for the Golden Reunion. And then on each side, the students had selected logos that would represent Murray State University. And then the coasters themselves also represent Murray State University logo items, sororities and campus lights and other activities that they would have been familiar with when they were here. And those are made out of acrylic and laser cut on the laser as well. A couple of other options that students submitted since we landed on the moon in 1969. Here is sort of a Murray State shield that you see in the background, and then you have the moon right in the middle, and then you have the Saturn V rocket in the center there. And here's another one. So this is a sort of a spherical look, and it has a variety of different logos or images that you might have seen from 1969 that those would have been familiar with. One of the things that Rustin alluded to earlier was the faculty involvement. And so all through this process, I'm encouraging students to think about certain things, or I would ask questions like, well, what if you did this? Or why did you choose that? And so in this case, the students just sort of had that wooden ball looking sphere. And I said, well, what if you designed a stand for that? So they of course designed an acrylic stand, and they folded it. We have a little acrylic bender there that we can use to heat that up and bend it up. Another project that we also do in that same class, this is a little more advanced than the previous one. It's called the 507 Mechanical Movements. And the 507 Mechanical Movements is a website. I think it's called 507movements.com. And back in the early 1900s, I believe there's a book called 507 Mechanical Movements. The webpage takes those movements and at least gives you a graphic representation of those. And in some cases, it's a basic two-dimensional line drawing, and it might be animated to kind of give you an idea of what this movement looks like. And these movements could be gears or pulleys or cams or linkages. There's a variety of movements that are there. And so as mechanical design students, we want them to start to investigate and look at some of these. And so, Rustin, if you'll flip to the next slide while you're...
Oh, sorry, I was looking at questions. I'll get to them after you finish these. Rudy.
Yeah. So over on the left, you'll see sort of that static image that you might see if you were to visit the website or look in the old book of 507 mechanical movements. And so I asked the students to find one of those movements and then interpret that in a way that can be built in a 3D model to make sort of a desktop diagram or representation of how that movement works. So in the middle image there, you'll see that's a SolidWorks screenshot or a rendering of this movement number 31. You can see that's a worm gear. And then on the far right, you'll notice that that's the physically produced prototype. Some of the pieces have been laser cut on the laser, and then the two white pieces in the middle of the actual gears were produced with 3D printing. And this was one of the few that actually worked the first time. So a lot of times students don't get them right the first time, and that's okay. We do give them a chance to go back and modify to actually get it to function properly. Here's another movement. This is movement number 120. And you'll see in the middle image there that it doesn't look exactly like the image over on the left per se. And so I do give the students a little bit of flexibility. I'll let them sort of talk me through why they think they can make a change to one of these movements. And that just gives them the ability to sort of practice those soft skills of discussing their design and why they made certain decisions within the context of the learning experience.
Hey, Rudy, we got a couple questions here. The one we can answer, I think, pretty easily for both of us at the start here is from Brett. And it says, how many lasers do students have access to? So I'll let you answer yours first.
Okay. In our prototyping center, we actually only have one laser in-house. There is another building that has another laser. They're both the exact same. We do ask that students schedule time on the laser, so we know when they're going to be on the laser and about how long it's going to take them. And we also ask that they work with a partner just in case something were to happen while they're utilizing the equipment.
How do you do that scheduling? That's part of his question too.
Usually within the context of the classroom. So we will just do a basic Google Excel sheet and students will fill in a time slot. Okay.
Brett, I can tell you, because I'm going to have some laser cutting examples too. We actually have 3 lasers in our Boilermaker lab. One is 75 watts, one is 80 watt, and one is 150 watt. Our largest laser can actually take a full 4 foot by 8 foot sheet of any material. We mostly use tempered hardboard now, which works a little bit better than plywood for us, and I can discuss that later on too. And then we actually use our lab. We have a lab manager. He actually integrated a free piece of software called Lab Manager. And we have a QR code on each of our machines. Students can go in, scan the QR code, or they just go to the website if they're remotely somewhere, and they can reserve the machine way ahead of time for as long as they need to. So that's how we do reserving time on lasers. So there's that question. A quick one, Cassie asked, could you do the Catapult project using 3D printing instead of laser cutting?
Absolutely, you could. In fact, that's how we started this initially. We were doing all 3D printed catapults, and we didn't have a laser at first. And then later we purchased the laser and decided to start moving into the laser. So yeah, absolutely, you could do a 3D printing one.
And Roger asked, we already answered how many lasers we both have, but how many printers do you have, Rudy?
Oh, I think just in this building, in the Rapid Prototyping Center, we have probably 6 and probably 8 in the other building.
Me here at Purdue Polytechnic New Albany alone, I got 2 in the classroom. I think that's important. No, I got 3 in the classroom now. 2 FDMs, 1 SLA, and then we have a closet that has 5 FDMs in it, and then we have a large FDM inside the Boilermaker lab. So whatever that adds up to is how many 3D printers we have. But we do have FDM and 1 SLA. We have the Form Labs 3 or Form 3 by Form Labs. So, Rudy, you just have FDM or do you have SLA?
We have both FDM and we have 1 SLA machine. Yeah.
Let's see. I got a question from Muffy earlier. Spends time teaching the difference between groups of 2 versus teams. I guess maybe teams. He means teams is more than 2, maybe. He also asked, how do you pick your groups? Or does it even matter if it's teams versus groups?
Yeah, that's a great question. I've tried a lot of different ways to choose teams. I have I've done it by allowing the students to choose. I've also done it by just random selection to, because as you suggest, you don't always get to choose your teams in the workforce. So I've done random selection. I've let certain students sort of do like team captains if they want to elect who they feel like is a team captain, and they get to choose, sort of like the backyard school style. I try to let the students have some input in that. That way they feel a little bit of ownership in how they selected their team. But it doesn't always work out really well for everybody.
I'd have to agree with all that too. It just depends on the class, what kind of students, what we're trying to cover. I probably go with randomization early on, freshman, sophomore. More often when I get into junior, I know the students, I know their skills, technical and soft skills a little bit better. So sometimes I can arrange the teams to spread that skill level across the teams. So I would agree with that. So Rudy, I'll let you go on a little bit more, and then I'll look at these questions. Maybe we can answer them as we go along.
Yeah, it looks like they're piling up, and that's pretty awesome. So I'm just going to talk fast and just sort of blow through these, and I think you'll have access later on. So you can always just come back and look at these, and we can start a dialogue outside.
Here's an easy one as you go along. How large are your classes, Rudy? That one just popped up. That's an easy one.
We have a maximum of 20 because we have a maximum of 20 CAD stations. Murray State University is a relatively small institution, so we don't have large classes anyway. On average, we have between 10 to 16 students per class. So that really does help out with this.
I would say mine are anywhere from 10 to 25.
Yep. Okay. Let's see. EGD 404 is a junior level class. This is where they're first learning to use our CNC router. We have an Axiom AR4. It's a relatively small router. It's 2 foot by 2 foot. I will warn you, though, it's not enclosed and it's extremely loud. So if you're looking at purchasing routers, then those might be some things to consider as you look at those. This is an individual project. I call it the one board challenge because I give them one piece of pine that's nominally 1 inch by 8 inches by 96 inches. And then they are supposed to design and manufacture something that is functional. And so if you go to the next slide, the first example there is a table. And this table actually serves multiple purposes. So if you'll flip to the next slide, yeah, perfect. It's also a charcuterie tray. And a lot of our students had never heard that term before. So he had to explain that it's a tray for your meats and cheeses. And so you can see here that this is just one of the examples that a student might come up with using SolidWorks to design this and using the router to manufacture this. He's got multiple pieces and he's got some interactions and sort of multiple functionality there. And you do, of course, see a range whenever you give students some creativity. You'll get really basic things and you'll get some that are super advanced that you have to sort of reel them in a little bit. Also in that 400 level class, we do a project called the Marble Bridge game. I happened to be in the library looking at old wood projects, and I came across just a really small idea for a game where you basically cut a marble into some sort of shape. And then the idea is to flick the marble through an arch and get some sort of point value. And so I had the students design one of these games, and I gave them a little bit more criteria. I said I had to have 3 arches, and they needed to be labeled with point values, and there needed to be some way to collect these marbles after they had sort of passed through the arches. So they get a variety of CAD software. Most of them are using SolidWorks. They're using the router. They can use the laser. So here's one of those examples of that. This was your classic King Kong versus Godzilla. So you can see on the right image there, the 3 arches. This is where the marbles would pass through. And this student set it up so that if one of the marbles hit Godzilla or King Kong just right, it would actually knock them over. And if you could knock them over, you immediately won the game as opposed to collecting a certain number of points. The image that you see on the left is the student's toolpath inside of VCarve. That's the software that we use that interfaces with our CNC router.
And I think this is the first project that you mentioned the router. So you guys have a router. I'll also mention that we have a Carvey, which is a enclosed router made by Inventables that you'll see some stuff. We also have a very large open router that's also has interchangeable heads, and one of the heads is a plasma cutter. So if we're kind of talking about those machines. And then I guess in my building, we actually have 2 very large industrial 250K a piece CNC mill and CNC lathe that our lab manager uses. Everything else students have access to. So
Also in 404, I do a project called an automaton. That's a sort of a weird word for a lot of people. They haven't heard that. It's basically just a machine or a control mechanism that repeats motion. Kinetic sculpture would be another word for this if you're searching for those type of projects. But students are tasked to design a functioning automaton. And a lot of times that will incorporate some of the 507 movements from the 200 level class. And sometimes you'll see some of those mechanisms reemerge in their automaton. So here's a couple of examples. The first one is a helicopter. And if you're looking at the image on the right, as someone would turn that crank, it rotates a shaft. There's a cam connected to the shaft, which then pushes a shaft onto the helicopter. And so it will go up and down as you rotate the crank. And also there's a little bit of friction in there. So the helicopter will sort of turn around and spin as well in that automaton. This next one has a large cam at the bottom and lobes that would be pushing these pushers up and down. On the top, if you're looking at the image on the left out of acrylic, they had laser etched the Murray State University logo in the top, and it was supposed to sort of look like this waving teardrop pattern as you rotate that blue crank.
Rudy, I can get you a couple questions here before you move on to your last one here.
Yeah.
Glenn asks, how do students define dimensions for your project? Do you set them for the sense? I think maybe it means like criteria maybe, and go ahead and answer that.
Yeah, so if I'm just, for the most part, I'll let the students choose what those sizes and interactions of components need to be. I think for me, that's part of the challenge to them is that I don't give them the size. So in a lot of assignments leading up to this, we may give them, to practice modeling, we would give them an isometric view or a drawing that's got very specific information on it, and they're going to recreate that. These project-based learning experiences sort of flip that a little bit, and the student has to start thinking about what size do I create those objects? And usually it's because of limited material. So, on the Catapult project, they've got that 1 12-inch sheet of plywood. On the automaton, they might have a 2-foot sheet of plywood. They may have one board. So they're going to be limited in their amount of materials. And I always pull in an industry thing and say, well, when you're designing for things in industry, you're going to be limited on the materials that you have as well. So you have to make design decisions based on what you can afford and what materials are available to you. I hope that answers the question. It may not.
I think it does, and I would agree 100%. That would be my answer too right there. Another one we have from Melissa is, how would you, maybe we should have saved this one. Miss Melissa, I'm going to save this maybe towards the end. How would you adapt for distance learning? I promise I'll get back to that one, but that one's interesting.
Yeah, definitely need to address that one.
Brendan Murphy said, what resources do you use to help students successfully manage time, improve soft skills, and complete these projects? That one's pretty deep too. You want to save that one for the end, maybe, Rudy?
Yeah, we'll come back. I'm not going to say I'm the best at but I've learned a lot over the years, so I can shed at least some of my personal experience with that.
I'll leave those open. I'm not dismissing those. And then we had one from Muffy. Do you have project grading rubrics to share with us? I can answer real quickly. For me, the projects that you're going to see, that is part of the project description handout. I can share all that stuff with anyone, and I'll let Rudy answer that one.
Yep. I also have some rubrics that I can use, and I've developed, a variety of things over the years for that as well. Okay, senior design. I've done a variety of things after taking over senior design the last couple of years, and I've tried doing a project with an actual client, and that proved to be quite stressful for a number of reasons. We've done some really simple projects, and some of the feedback I got from the students said, "Hey, this is too easy for us at the senior level." I've tried to allow the students to design their own thing. And it could be something that's new or innovative, or something that's an improvement on an existing product. And then this past semester, we were doing a little bit of a test with the SolidWorks / Dassault Systems 3D Experience platform. And so we had sort of dialed back the level of projects so we could focus a little bit more on the platform experience. And we were going to redesign some wooden games. And then that COVID thing caught us right in the middle of it. But I can show you where we got with that before we left. So at the senior level, we give students a lot more choice in terms of what software they want and what access to tools they want to use and that sort of thing. But a couple of years ago, we had a student group who's the grandmother. She had some challenges in grabbing things. She had a little bit of arthritis in her hand. And so this group wanted to develop a mechanical assist device to help her hold things or grab things. And so this was sort of the mechanism they got. And you can see that that almost all of that is 3D printed. We did a laser scan of her hand, and so they were designing the components to fit this woman's hand, specifically to her. And to my surprise, they were able to get it to work. We did not get to a point in that semester where we could actually have her test and get some feedback about how well it worked, unfortunately. Another project, when I gave students the option to just sort of come up with what they want, I had a group of students who like to camp, and they wanted to go out and hike, and then also to have a way to cook their food, some portable cooking system. And so they tried to design something that would fit just in a small duffel bag where they could go on an easy day hike, set this thing up, build a fire, cook some food, and then pack it back up. This is the example of the wooden games that we were going to redesign this past semester. The game on the far left is called Puck It. You're trying to use the elastic cord to flick those little pucks through a hole in the center. The top right game is called Klask. I think it's a Swedish game. And the bottom right game is called Oh Snap. And so these were prototypes. We had just gotten to producing these right before the virus sort of shut everything down, and we had to, figure out a new way to do things.
Speaking of virus, Ed asks, are you planning to teach remotely in the fall semester?
From our standpoint right now, we're hoping to hold classes in person, and we're sort of thinking that students are going to be back here in a couple of weeks. And but in the back of our mind, we are also thinking, if we have to go remote learning, how would we do that, and what would that look like?
And I can answer that, Ed, too. We're doing like a hybrid approach. It's up to the instructor to choose how they want to. They're encouraging in person with safe distancing and guidelines and all that. Two of the projects that I'm about ready to present, 2 are in the fall, 2 fall classes, and 2 are spring classes. So I don't really know about spring yet. I'm not looking at that yet. But the 2 fall classes, I still plan to do both projects that you'll see here in a little bit. What I've done is I've taken them from a team-based projects, and we've moved into individual-based, and we've purchased more material and supplies. So if we do have to go home, students can take everything with them, and they can still do it at home. And you also see that I use Solid Professor already, so you can do that remotely. And then also we can remote desktop in for SolidWorks. So students have the ability to do that, or they can check out a license. If they get here with a personal computer, they can install SolidWorks, borrow a license for a month, come back if they need to. A lot of students choose to do that also. So hopefully that answers Ed's question. And then I think we can answer Joshua's here real quick. I'm working with a new program with Applied Engineering and would like to add a laser cutter or rough cutter. What would you suggest to get? I can tell you that we have a universal laser. It's kind of on the top end of the line. We love it. It's really good. It's our strongest. It's 150 watts. It can cut through pretty good thick material, acrylic, wood, everything like that, not metal. And then our other 2 lasers, including the big one that I talked about, are by Rabbit. It's a U.S. company. They're a little bit cheaper made, I won't lie. They're a workhorse for us. We do like them. The other thing, before Rudy answers, I would say that there's a website, Anawa. I think it's anawa.com. I can look it up here at the end. It is hands down, it's not a US-based website, but it is hands down the best website I've ever found for comparing 3D printers, 3D scanners, and 3D lasers and carving machines out there. They do a great job. It's probably the most detailed website there is, but I think it's ANIWAA, I believe.
Yeah, good stuff. Here's what I would say to Joshua. I love talking about this sort of thing, and I try to dive in and get a little more information in the background. So if he wants to send me an email, I'd love to talk about it. In terms of lasers, we have the Epilogue Mini, but like Rustin said, the Universal is a great laser as well. There are some other options out there that may be cheaper depending on what level of cutting and engraving you want to do that you could look at. In terms of routers, we have the AR4 for wood routing. In our machine tool lab, we have Tormach machines and we have Bailey machines. If you're going to think about cutting metal stuff on the wood, we also have an Inventables CNC router as well that we like really well.
That's who our Carby is through, is Invincibles. It's just fully enclosed. So you really, like Rudy said, you got to think about the material that you want to cut, the thicknesses of the material, the size of the material. Those are probably like three real, and then your cost, right? You got to think about cost. And then envelope size. Do you have the room to put these machines to? Would be some of the things that you really have to consider before you purchase something like this. Roger asked, what is the cost of your different lasers? I honestly don't know. In my case, I don't know between the three. I mean, you're talking thousands for our three lasers for sure, because our smallest laser platform is our universal, and it's still 13 by 18 inches. So it's still pretty big, and you got to have external exhaust. So I don't know. Rudy might know prices on his. I don't know mine.
Yeah, I feel like our Epilogue Mini, and it's a 12-inch by 18-inch cutting envelope and has the filtration system and air assist and that sort of thing. I feel like it's around $12,000. It's a pretty expensive machine.
Yeah, you're in thou. I don't think I know of a laser cutter that's under $1,000. I can tell you that. I don't think I know of one under $1,000. There are some desktop ones out there now. There was one that was a huge Kickstarter campaign that doesn't require exhaust system. It has a filter underneath of it. Man, I cannot think of the name of it right now, but it was still, I think, like $3,000. So
maybe the Glowforge.
Glowforge, yeah, the Glowforge. I think that's like the lowest cost laser cutter I've ever seen. It just doesn't go through very thick material, but you can do some pretty impressive stuff with it still.
Mm-hmm.
All right, I'm going to move on to my projects here. All right, I have 4 for you today. The first one is from a course called Tech 120. This course is typically taken by first semester freshmen. Every student in Purdue Polytechnic has to take Tech 120. So we get mechanical engineering technology students, electrical engineering, mechatronics, IET students, industrial engineering, and then computer graphics technology majors as well. So it's a very diverse class. All right. The goal is to introduce design process, engineering, and then rapid prototyping. It's kind of our overall goal, and just to get familiar with college and our building and how we teach. All right. We are applied engineering program. So it's different for a lot of kids coming in to understand that we're going to do a lot of project-based learning. The project is definitely a team project, typically 3 to 4 per team. To answer one of the questions earlier, this fall, everyone's going to do it individually. We were able to procure and borrow many more of these Lego kits that I'm about ready to discuss. So that's going to allow us to do it individually. But overall, the objective of this project is to design, build, and test an autonomous robot to complete a challenge. All right, that's your top level objective here. We usually change the challenge every 2 to 3 years. All right. Me and another teacher teach the 2 sections of this class. 1 year, the challenge was to draw your initials of each team member within an assigned writing zone on a poster, and you'll see that here on the next slide. And the other one was the last 2 years was to navigate from a starting position to a collection site and to collect a sample. And you could really say that's like a search and find kind of a challenge. The materials we use for this is the Lego Mindstorms EV3 educational kit. It's amazing, but they're about $450 a piece, so they're pretty expensive. And then the Boilermaker lab access, and I've kind of already discussed some of the rapid prototyping equipment we have in there. We also have a supply room in there with acrylics and woods and foam boards and fasteners. We have all your typical subtractive manufacturing equipment, saws and band saws and table saws, chop saws, sanders, metal forming equipment, casting equipment, industrial CNC. So this is a pretty big Boilermaker lab. And I will say that our students from day one have access to this lab as long as they pass the safety quiz. So it's pretty special place. But for this project, we really try to get them to use the 3D printers and the CNC lasers. The software, when we have them do the designing of their robot, we actually have them do Lego Digital Designer. It was made for K through 12, right? So college students should be able to kind of figure it out and tinker with it on their own without training, all right? Because they haven't had a CAD class really at this point, or they're in it at the same time. And then the Lego Mindstorm programming language or programming software, and then your printer laser control software, of course, we have that. And this is a 16-week project. It starts from the very beginning. However, what I'll say in this class is we kind of do a lot of hand-holding with this project. Those 2 challenges that I tell you right there, they're really broken up into 5 different stages. So it's not like hey, you got to be able to do the search and find at week 2. You do that at week 16. And through the 16 weeks, we are training you how to do the programming. You'll design your robot, do all that other stuff leading up to it. But you could say it's a 16-week project. You can see the Lego EV3 kit over there on the left image. It comes with a suite of sensors. It's pretty amazing stuff. It's got 2 large motors, a small motor. It's got 2 touch sensors. It's got a color sensor, a gyroscope, and then an ultrasonic sensor. All right, so they can use those however they want for these challenges. This is a very open, creative. We don't tell them what the robot has to look like, for these challenges, or what sensors they have to use. That's all up to them, right? We just give them the end goal challenge. There's all kinds of little Lego bricks, obviously, that come with it also, and tank tracks and all kinds of stuff. But that middle top image there, that is the playing board for the initial challenge where they have to write their initials. So every robot starts in the lower right-hand corner, and then autonomously they have to navigate to their zone, and then the robot has to write each person's initials. So it's pretty challenging. There's many different ways that students can do this, obviously, right? So majority of them put their robot on wheels and they drive it, right? They say, go forward 6 inches, turn 90 degrees, drive, another 6 inches, right? And then they have to do the code to write the initials. But we've also had teams who have went into the lab and designed and built a plotter system where there's no wheels at all. Everything runs on like a carriage system, kind of like a printer. And they literally lay that thing down over the entire board, excuse me, and they have the pin in the lower right-hand corner, and then it moves just like a printer would, in X, Y, and Z. So it's pretty impressive, the stuff we get out of them. And this is freshman first semester.
Rustin, a couple of questions there. One from Roger. Are these students borrowed by the students, or do they purchase those kits? And if they're borrowing, what might you do about sanitizing those pieces?
Yeah, so they are borrowed. They are ours. This semester, I borrowed some more from some other people that I know, and we purchased some more. They have to sign a contract. All right. So if they don't return it, they have to replace it. In 5 years, we've only had one student, and he actually had it stolen out of his trunk, but he still replaced it. Every other time we get it back. This year, I'm going to be gloved up and masked up when they return it individually. We'll have probably a sign-up sheet, and individually they'll bring them outside my office. And I'm probably going to have a bottle of Lysol, and I'm going to spray the whole thing down. But they're going to be in their possession for the entire 16 weeks. So maybe that will answer that question. Only they will have them in their possession once I give them to them.
Okay. One more question from Ryan.
Sure.
How did you get the mechanism on the bot, and did students design 3D print hubs?
They did. Those are 3D printed wheels that a team wanted to go with that direction. I believe they found those on Thingiverse. So I'm a big believer in not reinventing the wheel. We teach students right out the bat about Thingiverse and GrabCAD, all those 3D repositories. And we encourage, it's not cheating to us if you utilize the existing product in a different fashion, right? That's innovation half the time. So students took those, they scaled them how they needed to, figure out a way to attach it to a Lego. And then the first part of that, what was that, Rudy? The
3D printing the hubs, or how did they get the mechanism on there?
So they have to design the robot. So they design the robot and they assemble it however they want. If you look in that lower left-hand picture there, all the pieces come individual like that. The brick, which is your computer, is that big thing there. That's, that does all the processing. So, but they design the robots and build them themselves. Excuse me, I got a little tickle in my throat.
Rustin,
I'm not used to talking so much. We're not in class yet.
Yeah, no kidding. Looks like we got about 10 minutes. So if you want to fly through your last couple of projects.
I will. The second one here is in our intro CAD class. This is a much shorter project. It's the only project that's not 16 weeks. It's about 2.5 weeks. It's a reverse engineering project. And at the core of it is I asked them to take an item from their daily life, reverse engineer it, and add value to it. And you can add value through changing the form, fit, function, any of that stuff, or adding additional features to it. And this is kind of a great little example. I love this. We had a kid who was really into Mustangs and cars. He wanted to incorporate that air-fuel ratio gauge that you see in the bottom right there into one of his vents. So he popped out one of the vents, reverse engineered it. Remember, this is usually first semester freshmen. Modeled it in SolidWorks. You know, we were teaching them SolidWorks along the way. This project's usually in the back half of the class. And then, you know, they have to rapid prototype it. He actually did it a few times to refine the design, and you can see the final product there. It actually installed, and he actually still has this installed in his car. So it's kind of a neat thing. These other two images here, this is a vast array of different projects that have come out of this over the years. Anything from, you know, I can use my mouse here. This is, you know, where you put treats underneath of these cups, and then a dog has to be able to move these to get to the treat. We had a student who wanted to design a personalized Connect 4 board for his girlfriend for Christmas, which is over here. So laser cutting, a lot of 3D printing. This class is usually their first, for most students, their first time dealing with 3D printers. So they learn a lot of tips and tricks and lessons learned from 3D printing here. So we got all kinds of stuff on that. This is probably my favorite project. This is typically taken by second semester freshmen and typically only MET majors only. I call this the Cornhole Catapult Project. The objective is to design, build, test, and document. All right, those are four very key things there. The document's probably the most keyed on this class. A catapult with no commercial off-the-shelf, that's COTS, fasteners, and or adhesives that can replace a human thrower when playing cornhole. All right, hopefully that gives you a pretty good idea of what's going on here. This is definitely a 16-week project, and the constraints on this project is the instructor supplied materials. So every team is given the same materials, and that is one sheet of 4 foot by 8 foot by 1/4 inch thick tempered hardboard. It cuts really well on a laser. 8 foot of nylon braided rope, 8 foot of nylon bungee rope, 1 foot of 1/2 inch diameter steel rod. Then they get this little 6-inch leather sheet, and then they can use they get a little 1-inch HDP tile that they can cut out also. But that's the only materials they have. So you can imagine these catapults have to fit together really well. So the class covers fits, you know, your clearance and your press fits and interference fits. So they have to utilize all that knowledge that they learn in class when they're designing these catapults. You can see the CAD model on the left for this one, the physical prototype. This team actually did 2 prototypes. They cut it out of cardboard first. So they went and found the same thickness of cardboard at a store as the hardboard that I gave them. They cut it all out and make sure it fit all together correctly, and then produced the final version. You can see the drawing package on the right. That's really what this class is a lot about, is to create engineering drawings in accordance with standards and specifications, specifically Y14.5. This had 32 sheets. This drawing package was a 32 sheet drawing package. So very detailed, very, very detailed. This is another one from last year. This got second place. You know, they can be as creative as they want in the design of the catapult. That's what makes this really interesting and fun project. This one actually had 45 sheets. This is second semester freshmen. These are 11 by 17 D-size sheets, 45 of them.
Rustin, I've got a question for you.
Sure.
We've got 5 minutes. Can you talk Mountainboard project in like 2 of those and leave 3 minutes to get to some other questions?
I will.
Awesome. Thank you.
All right. So this is a junior year Mountainboard. This was to prepare students for a 2-semester industry-sponsored senior capstone, which is what we have. The challenge here was to increase product value, safety, stability, and manufacturability of a current digital design mountain board. All right. So you might be saying, what is a mountain board? Think of a snowboard and a skateboard put together. All right. So you can kind of see an image of one right here in the left right here. All right. So I got this project originally from this SolidWorks mountain board student guide that SolidWorks used to put out. We would work through this guide to learn some advanced SolidWorks skills or CAD skills. I did that for the first 3 years, and then I would move into the project, right? Or they would start working on the project at the same time. Last year and this spring, I'm going to use Solid Professor because they've stopped updating the mountain board guide. But overall, the scope change project overview is requirement identification, conceptual design, or where they get all the ideas out of the way, right? Some sketching, stuff like that. Move into a PDR, where they're going to produce a low fidelity prototype, and then also a CDR, which is a critical design review. And there's rapid prototyping all along the way. Also a mind map that they use for a lot of the brainstorming and project management. These are some of the PDR elements. So I just said mind map. You can see the mind map here in the upper left-hand corner. This is, a brainstorming tool, but I also encourage them to use it as a project management tool. The nice thing about this project is no student really knows what a Mountainboard is, so they have to do a lot of background research. And when they do that, they tend to also create kind of a brand around their team. So you can kind of see they'll do logos a lot of times. So Board Up was a brand that they did one time. Playboard was another, and they create logos and everything for it. So it's kind of neat. They do a lot of project management tracking here, Gantt charts, simple Gantt charts. This is a junior class once again. And then they're doing a lot of decision matrix at PDR, where we're trying to design on what concept will we go forward with, all right? And I act as a customer, all right? So I guess I should have said that too, as I do a lot of role playing in this class. I am a customer, so when we do PDRs and CDRs, they're very formal in nature. And then here you can see CDR elements, high fidelity digital prototype moves into a high fidelity physical prototype, into very detailed drawing packages for documentation. This was a team who wanted to fold the Mountainboard in half. That was quick. I can go in more detail later on that.
That was quick. I really wish we had another full hour to talk about this. That would be amazing. So I'm in favor of skipping this slide and then just getting to people's questions. So if you want to go to the very last one, it's got our email addresses on there. And that way people can get a hold of us.
You can get a hold of us through the system too. So
yeah. Okay, let's go back to Melissa's question. How would you adapt for distance learning?
Well, I kind of mentioned a little bit, Rudy, on mine is I moved away from team-based and I required more materials so I can send it home if I need to. And I'm also going to do any lecturing remote. So we will do all lecturing remote. And I also use Solid Professor, which helps a tremendous amount for this.
Great. I think that's a great answer. Perfect. Brendan, he asked earlier, what resources do you use to help students successfully manage time, improve soft skills, and complete these projects?
The first one I just mentioned there in the Mountainboard project is the mind map. The website we use is Coggle, C-O, is it two O's or two G's? I think it's COGGLE.it, IT. It's free for their basic. It is awesome because students can work on it in real time and also collaboratively. And also they have to add me. So I get all kinds of notifications when they're working on it. I can leave feedback. So they use that for not only brainstorming, like I said, but also project management. So they can track milestones and all that kind of stuff in there. And they can do it remotely. So Coggle is a really, really nice tool.
Yeah. To add to that, one of the things that we do, we have a weekly team meeting. I sit down with the teams. And one of the things that we've tried to implement recently is an Excel spreadsheet that each week they have to identify a task, assign a person to that task, and put a deadline on it. And then when we come back the following week, we say, okay, Rustin, did you complete this task by this time? And it gives an extra amount of accountability in there. And it does take a lot of work to keep students on task with these things. For our students anyway, they get a lot of time outside of class to work on them as well as in class time. And so it does require a lot to work with them and help them figure out what these time management skills are. And that's part of the soft skills that we're trying to teach them as well.
For kiddies there, Rudy, as you're reading that, I kind of glanced over it. And I guess I should also say it kind of ties into the remote. What are we going to do in the fall? The projects that I showcase that actually require a student to come in to use our equipment, I'm planning to still do that. Like I said, they'll do it on an individual basis. They'll have to reserve the machine, so it's only one person working at a time. If all that goes away and we have to go remote and students can't come in, what will happen is in my rubric, one of the criteria, usually most of my rubrics have 5 criteria. One of them is always a physical prototype. I will just remove that line item from the rubric and it will just be a digital prototype, which is usually the one right above. Some classes, they're combined together, but I'll just separate it. And I'll just remove the physical build portion of these projects. I hope it doesn't happen, but that's the best I can do. I think it's important to still do the digital prototype.
Yeah, I agree. And I would probably do the same thing. They can still get to through the design phase. They may not be able to access the actual manufacturing, but I have my students create a manufacturing plan. So they're supposed to tell me what steps they would go through to get to how they're going to make this thing. And so what I've considered doing this fall, and I haven't completely wrapped my brain around this just yet, is they submit the whole process to me, and then I actually produce the lab, provided I still have access to get to our lab space. I may actually do the work for them and then mail it to them in a kit, or if they're local, they might be able to come by and pick it up off the doorstep.
Yeah, and I can kind of tie that. So last semester when we had to leave early, I've already talked to some students who finished the digital prototyping from the spring. Their plan is when we come back here in the fall, they're going to come back and they're going to print or cut the stuff still, because they want to see their catapults, right? They did the whole digital design. They got the equipment, or the material. They're going to finish it out so they can take that home with them. Because I don't keep most of the stuff in house. Students, whoever wants it from the team takes it with them. So I saw a question. Did you close a question out, Rudy, there?
No, I didn't close it. It is 2:02. I do want to thank everybody for being here. I guess we can hang out and answer questions if we need to.
Sorry, I do want to answer Cassie Anderson if you're still here. Yes, my email does not have an R at the end of Webster. Purdue couldn't afford the R, I guess. So it's rwebster@purdue.edu. It's silly. So yes.
Nice.
I think that's all we got, right?
Thank you.
Thank you everyone for being here.